So again, we've got our light bulb test, but now instead of one beaker with one light bulb, we've got 12 jars with 12 light bulbs, and we'll look at a lot of them. First of all, over here on the right, distilled water. We already know that that shouldn't light up, and in fact it doesn't. We also know that 0.1 molar sugar should not give any light, should not be conductive, and I can screw this light bulb in and nothing happens. Okay, it is also dark. Now, next to that is 0.1 molar sodium chloride. And when I screw in that bulb, I get a bright light, indicating a lot of ions. Now, next to that is sodium chloride, but only 0.001 molar. And when I screw that light bulb in, it's much dimmer. In fact, you might not be able to see it. Let me undo the bright one. A much dimmer light. By the way, over here on your left is solid sodium chloride. I screw that light bulb in, no light. Why is that? Well, the ions can't move because they're in the solid state. Okay, now we also have 0.1 molar HCl. I screw that bulb in, again a bright light, okay, indicating a lot of ions. Down here is 0.1 molar acetic acid. Much dimmer. I'm not sure you can see it. Let me undo the HCl. Some light, but much dimmer, indicating many fewer ions. So again, we have a measure of the number of ions in solution by the brightness of the light. Let's look at the results of our experiment. We tested the electrolytic properties of 8 materials, which appear in the first column of the table. The experimental result was the brightness of the bulb. We can then infer the number of ions present and the type of electrolyte. We already knew that with only distilled water present, the bulb was dark. This tells us there were no ions present. Water is a non-electrolyte. 0.1 molar sugar also produced a dark bulb, indicating that no ions were present. We would classify sugar as a non-electrolyte. On the other hand, 0.1 molar sodium chloride produced a bright bulb. This indicates lots of ions. Being an ionic compound, we would say that sodium chloride is a strong electrolyte. 0.001 molar sodium chloride produced a dim bulb. Remembering that the brightness of the bulb indicates the number of ions present, we would conclude that there are few ions in solution. You might be tempted to classify this as a weak electrolyte, but that would not be using the term correctly, chemically. The dim bulb is consistent with the lower concentration of salt, but all of the salt in there, in fact, went to form ions, so we would still classify this as a strong electrolyte. Solid sodium chloride did not produce any light from the bulb. We might conclude that there are no ions present, but really we should conclude that there are no mobile ions present that are free to move around in the jar. That is because in the solid, the ions are locked in place in the crystal lattice. So to avoid any confusion, let's not classify this one. 0.1 molar HCl produced a bright bulb. So we conclude that there are lots of ions, and this is a strong electrolyte. At first, this should be puzzling, since both hydrogen and chlorine are non-metals, so we would expect a non-electrolyte. But something clearly different is happening here. We'll have to come back to this when we talk about acids and bases. Finally, 0.1 molar acetic acid. This solution produced a dim bulb, which indicates few ions. Notice, though, that the concentration of acetic acid is the same as the concentration of the strong electrolyte, hydrochloric acid, but fewer ions were formed. We will characterize this as a weak electrolyte. Notice that there are 2 ways to get a dim bulb. First, you can take a strong electrolyte like sodium chloride and only put a little bit into solution. That only produces a little bit of ions. Or take a material that only makes a little bit of ions on a percentage basis. This highlights the difference between concentration and strength. In everyday language, we use concentration and strength interchangeably. You may buy a cup of coffee and say, "This coffee is too strong." But what you really mean is that the molecules responsible for the flavor are too concentrated. In our chemistry language, concentration tells us how much material goes into solution. Strength gives us a measure of the percentage of that dissolved material that goes on to form ions. This leads to the distinction between strong, weak, and non-electrolytes. A strong electrolyte is a material that goes 100% to form ions when dissolved, regardless of the concentration. Ionic compounds would be strong electrolytes. A non-electrolyte forms no ions when dissolved. This would be most covalent compounds, but not acids or bases. We can define a weak electrolyte, which is somewhere in between. When dissolved, it partly forms ions, and it partly stays as neutral molecules. Some acids and bases are weak electrolytes. We'll look into this further when we study acids and bases.